Ya me está gustando más de lo normal. Esto hay que tomarlo sin ningún apuro.
Despacito, quiero que sonaba menos despacito. Firma las paredes de un laberinto. Descubierto tu manuscrito.
Okay, on Monday we left off talking about the transverse wave. And the transverse wave is what you get when you have some kind of repeated disturbance that's transferring energy. So like the pendulum swinging back and forth, or the mass on the spring going up and down. You could also create it just by taking a string and shaking it up and down like you see in this picture. That's you putting in some kind of energy and causing it to propagate down that string. And the reason why we call it transverse is because that string would then move perpendicular to the way that the wave is traveling. And if you kept moving the string up and down, you'd get a picture like on the right. And we talked about all the different properties that come with that transverse wave. So you've got things like your crests and your troughs, and in the middle is your equilibrium position. You can count how many waves you have, and we call that the wave number. So 1 and 2, or 1, 2, 3, or 1 and 2. We talked about the amplitude as being just the distance from that equilibrium position up to the top. We talked about the wavelength being peak to peak. We talked about the frequency being how frequently these waves show up. And we didn't explicitly say it, but another way to think about frequency is the number of waves per second. It's measured in hertz, and a hertz is really just 1/seconds. And then we related frequency with period, where period is how much time it takes for one wave to go by. And we alluded to the fact that they're inversely related with a formula like this. T equals 1/f, and F equals 1/t. So if we take our spring and just give it a shake, we create a transverse wave that makes the matter move perpendicular to the way that the wave is traveling. But what if we have a spring and we take a bunch of it and we just bunch it up? Then that means the bit that we haven't bunched up is going to be stretched out. And then we let go. That bunched up bit is going to travel across, but as it moves away from this end, this is going to become stretched out. And you're going to have a propagation that goes down that spring parallel to the way that it's moving. We call that a compressional wave or a longitudinal wave. It looks sort of like this. So we can see that you've got this ripple that goes across in the same direction that the wave is traveling. And if it was a full-on wave and not just a single pulse, you could see that these bands look like they're traveling to the right. But in the same way that the string isn't actually traveling to the right with the transverse wave, the wave's not really traveling to the right in this picture. I should say the matter's not really traveling to the right. The wave is traveling to the right, but these dots indicate that the matter is just going out and back and out and back. So we call this a longitudinal wave, and this would be like sound. Sound is also a longitudinal wave. Your voice box shakes the air, those air molecules get compressed or expanded, and that propagates out to somebody's ear, which then shakes their eardrum, and you hear that as sound. In FET, I've got this setup here where I've got a speaker, which is sending a sound wave out to this person's ear, and that sound wave is a longitudinal wave. It's made up of compressions and rarefactions. Compressions where the molecules are close together, and rarefactions where the molecules are spread apart, and they oscillate between the two, and that oscillation between compression and rarefaction is what gives us our longitudinal wave. And it has a certain frequency because it is a wave. And so if I was to enable our audio right here, you would get that annoying tone. And that annoying tone is what this person is hearing when this longitudinal wave has a frequency of 400 hertz. But if I increase the frequency on this thing up to about 740 and turn audio on again, that new annoying tone is the new sound that they would hear. And so frequency determines pitch for our sound. Higher frequency, higher pitch, lower frequency, lower pitch. Whereas the amplitude of our wave, which is essentially how dark these bands are, or how compressed our compressions are and how expanded our rarefactions are, that determines the loudness of the sound. Much louder, annoying tone. Now if I have two speakers set up though, if I've got a top speaker and a bottom speaker and they're both sending out these sound waves, there's going to be a point in the middle, obviously, where they overlap. And you can see that there's a sort of pattern that exists in the spot where they overlap. You've got, your compressions and your refractions still, but you've got these bands right in the middle here, which look a little bit different from the rest of the wave. And in fact, if I was to put this person right here and enable audio, sounds like normal. But if I move him into one of those weird bands and try this again, it goes way down. Turn that off. And so there's some kind of interference that occurs when these two speakers are working against each other. And what that means is that if a compression matches with a compression, you get a bigger compression. If a rarefaction matches with a rarefaction, you get a bigger rarefaction. That's a hard word to say. But if there's a compression with a rarefaction, they're essentially going to cancel each other out. So this idea of interference works for both your longitudinal waves and your transverse waves, and I think it's a little bit easier to see it with the transverse wave, so that's why I've moved over to this simulation from PhET. And so if I send a pulse down this string with these beads on here, it's going to hit this ring on the other side, and then it's going to bounce back. And it's going to continue to do that for forever. But watch what happens if I put another wave in here. So now I have two waves in here that are both moving along this string. This wave on the right is going to hit this pole and come back. It's going to reflect the same way. And watch what happens once they get close. We now have a much bigger wave when they overlap. We have constructive interference. A crest and a crest combine to give you a larger crest, in the same way that a compression and a compression will combine to give you a larger compression. But as they separate, this is the wave that was on the left, it just passed right through. This is the wave that was on the right, it just passed right through. And they're going to continue, only now this is going to be a trough and this is going to be a crest. And when they overlap, they essentially cancel out. If I had been quicker, we would have had a more obvious example that they completely canceled out. And so you have destructive interference. A crest and a trough will cancel out to give you no amplitude at all as long as they have the same height. And you can go through and do all other different combinations, but essentially compression and compression, bigger compression. Rarefaction and rarefaction, bigger rarefaction. Same thing for crests and troughs, but if they're opposite, you're going to have to subtract the two. Continuing with this idea of interference, what if we had a tube and we sent a sound wave to the right and to the left, which I think is backwards for the video, but whatever. So what we could do is we could plot the amplitude, or how compressed and expanded the compressions and rarefactions are, and we would get a picture that looks like this for one set of frequencies, where we have maximum at either end and absolutely nothing going on in the middle, no deviation at all. But if we were to change the frequencies of one of those waves, or both, we could end up with a picture that looked more like this, where now there's no deviation at these 2 points, but a lot in the middle and at the ends. And we could change it again so that there are 1, 2, 3 different spots where it doesn't change. Or we could change it again so that there are 1, 2, 3, 4 different spots where it doesn't change. And then again, follow the pattern up to 5. These spots where there's no change at all, we call those nodes. And the points where they are kind of oscillating up and down, we call those antinodes. And so this is called a standing wave. If you've got two waves traveling in opposite directions and they overlap, and suddenly the wave doesn't look like it's traveling left or right, it's just going up or down, that's a standing wave. Same setup, just a static image now. It is still up and down or down and up. I've drawn both extremes in here. And the next one down is the same thing, up, or down, up, down. And so because the top picture is the fewest number of waves that we can put in that pattern, we call this the fundamental frequency, or the first harmonic. The next one down, though, is the next stable pattern that we have, and so we call that the first overtone. It's the first harmonic that we have after that fundamental, but more easily it's just the second harmonic. And then the last one would be the second overtone, the second one past that fundamental, or more easily the third harmonic. The other thing to note, though, is let's count the number of waves. We have half of a crest and half of a trough, so this is 1/2 of a wave, 1/2. Down here we have half of a crest, a full trough, and then the other half of the crest. So this is a full wave, 2/2. And then this one down here we have half of a crest, a full trough, a full crest, and then half of a trough. So this is 3/2 of a wave, or 1.5 is another way to think about it. So our formula that relates these frequencies, or these harmonics, should look like this, with a 2 in the denominator because we're always counting by halves. And we've got our harmonic number in the top because the first one had 1/2, the second one had 2/2, the third one had 3/2. So the frequency of this standing wave pattern depends on your harmonic number times how fast you're moving divided by 2 times the length of the tube. And we can play the same game if we weren't open at both ends. We could do this if we were fixed at both ends. We'd have a very similar looking formula, NV over 2L. And the reason why is because the pattern still ends up being the same, just shifted without the pinning point being in the middle to being at either end. But you can imagine this like a rubber band that you've held at both ends and you use your nose and you flick it, and you're going to have that oscillation that goes up and down. Or if you had pinched at either end and then you have somebody help you by holding the middle, you could flick either side and it would go up and down like this. Or you could pin it in 4 different places and have multiple friends help you, and you'd have a pattern that goes down on the ends and up in the middle, or conversely the other way. And the setup's the same way. First harmonic, second harmonic, third harmonic, fundamental frequency, first overtone, second overtone. So fixed at either end or fixed at neither end, they're exactly the same. The difference is going to come when you fix only one end. Then you've got a pattern that looks like this. And now notice we only have a quarter of a wave. Or in this one we have a half plus another quarter, so 3/4 of a wave. Or in this one we have a full wave, 4/4 plus another quarter, so 5/4 of a wave. In this pattern we're going 1, 3, 5. So we're counting odd harmonics. There are no even harmonics when we're fixed at only one end. And so our formula is going to look different. It's going to be NV over 4L. We're counting by quarters, and we have to remember that that N can only be odd. So these formulas are how you find the frequency for a standing wave. It depends on your harmonic number, how fast you're traveling, and the length of the tube. And you have to make sure you keep these 3 cases separate. Really just the 2 cases, because fixed at neither end and fixed at both ends are the same, but you definitely have to be careful if it's fixed at only one end, because you can only count odd harmonics. Those formulas really come from the wave speed equation, which is V equals F lambda. Your wave speed is equal to your frequency times your wavelength. And so if you have a wave that is moving at some speed and you increase the frequency, meaning you squish them together, the wavelength is going to decrease. So frequency and wavelength are inversely proportional. And so in the standing wave examples that we had, as you try to fit more and more and more of those antinodes in there, the waves are going to get closer and closer and closer together. And so you're going to end up with a larger frequency, but a smaller wavelength. And the wavelength is really just a fraction of that total length of tube. So for NV over 2L, for example, frequency is going to go up as harmonic number goes up, but if you plug it into this formula, you're going to see that wavelength should go down. So this is the wave speed equation. V equals F lambda. Your wave speed is equal to the frequency of your wave times its wavelength. Besides interference, another interesting thing that waves do is this idea of Doppler effect, and I think it's most obvious with sound, so that's why I put it in this video. And we've all had some experience with the Doppler effect, even if you didn't know it. It is that situation where you have a vehicle with some siren that drives past you, and the siren sounds different when it's approaching compared to when it's traveling away. And the reason why, I think, is explained pretty well with these animations right down here. So all the way on the left, you've got a red dot that's emitting sound. And so that sound wave is traveling out in every direction, and there's not really much to it. It's just equal-sized circles that are traveling out. But if the red dot is emitting sound and moving to the right, it's moving to the right while the waves are also trying to move away from it to the right, and it's moving to the right while the waves on its left-hand side are moving away from it to the left. And so we have bunched up waves on the right and spread out waves on the left. And as we know, frequency is really just how close those peaks are. So you have a larger frequency on the right and a more expanded frequency on the left. As we talked about, frequency relates to pitch. So another way to think about it is, as this siren's approaching you, it has a higher pitch, and as it's leaving you, it has a lower pitch. And in fact, you can go fast enough that you actually go faster than the sound that you're creating, and you can travel outside of those circles. That's the picture here on the right, when it's actually at some Mach speed, some speed that's greater than the speed of sound, in which case you wouldn't even hear that siren that you're emitting because you're past it and the waves aren't able to catch up with you. That is going to create a movement of air, which will eventually crash back in, and that's where you get that sonic boom that you hear about from things that are moving supersonic. It would be nice, though, to predict exactly how much this frequency changes by compared to what it would be if it wasn't moving at all. And so, of course, we need a formula. And the formula looks like this. So you've got your perceived frequency, which is the frequency that you hear, which is equal to the actual frequency, the frequency if you were standing still. And then you've got 343, which is the speed of sound, and that will change depending on what material you're in or like humidity or things like that. 343 is a good ballpark, but double check with your problem what the actual speed of sound is. And then you've got plus or minus the speed of the observer, divided by, again, that speed of sound, minus plus the speed of the source. And you want to make sure that you don't mix those two up. They're that way for a reason. But there is some notation that you can use that'll make things a little bit easier. So what you want to do is you want to say that movement to the right is positive and movement to the left is negative. That is just standard stuff that we've always been using. But what that means is that your observer, the person or thing that's hearing the sound, is always left of the source. So if that's the case, then what that means is you're going to use the top signs, plus over minus, when the source and observer are moving towards each other, and you're going to use the bottom signs when the source and observer are moving away from each other, so minus over plus. So if they're going towards each other, plus over minus. If they're moving away from each other, minus over plus. There are ways to simplify things. For example, if the observer isn't moving or if the source isn't moving. But I think if you keep your notation consistent and you draw a nice picture before you start, this formula isn't too difficult to work with. And that's a whirlwind tour of the longitudinal wave. It is most often seen as a sound wave, but it doesn't necessarily have to be. A longitudinal wave is any wave where the matter moves parallel to the way that the wave is traveling. We've seen that there's interference that occurs for a longitudinal wave, no different than in a transverse wave. We've seen that there is this idea of resonance, which is where we get standing waves. And resonance is really just putting in energy to get a pattern that doesn't look like it's traveling to the side. Instead, just looks like it's moving backwards and forwards or up and down. Another way to think about resonance is like on a swing. There's a reason why you kick your legs when you do on the swing. If you try to put the energy in the middle, you don't have resonance, and so you're going to mess up that wave pattern. You're not going to have a standing wave. But if you keep putting in energy at the ends where you need to, then you're going to have a standing wave pattern. And the last thing that we talked about was Doppler effect. The frequency that you perceive as something moves past you, or conversely as you move past it, is going to depend on how fast you're traveling or how fast the source is traveling. So that is very quickly a few things that you can have occur with sound. The next time we meet, we can look at other weird things that waves do, more geared towards light. And I guess I'll see you next video.